have feedback, or everyone should fill out this feedback form for Lucky's presentation, so we as a leadership team can get a better idea of what's working and what's not in these presentations. And hopefully I'll fill it out for me too afterwards. Oh, that's all my stuff. Okay.
Where is the form?
In the chat, Zoom chat. Okay. Hopefully everyone's back. I'm going to go ahead and get started. By popular demand, the intellectual glasses are on, and we'll go ahead and get started. Can everyone hear me okay? Can someone just like, cool, great. Okay, buck converters. If you're on this team, you've probably heard me talk about them at some point. Everyone in electrical has probably heard my spiel a couple of times. This is a little deeper. Even on mechanical, you've probably heard someone on the team saying, oh, the buck's not working. Have you tested your buck? How do you debug the buck? Buck, buck, buck. We hear that word a lot. So I'm here to demystify some of that, hopefully. Real quick, this presentation might feel a little bit dry at times. I tried to mitigate that wherever possible, but just to spice things up at the beginning, I threw in some peppers, which didn't load for whatever reason. Great, it didn't load. It's okay.
Google Slides is vetoing your joke.
Okay, maybe if I reload it, it can. There we go. All right, so spicy presentation, cool. So these are the key questions I wanted to cover with this presentation. Hopefully you'll be able to answer at least a couple of these by the end. First is, what is a buck converter? Why do we need them? How do we design one? And how do we improve them? So this is what I hope you get out of this. This is a lot of words, but hopefully by the end of it, some of these will be demystified. So I want to go over the general concepts of a linear versus switch mode power supply and the general parts of a buck converter. And I want you to be able to define some of these words at the bottom here, like duty cycle, EMI, ripple, voltage overshoot, filtering, efficiency, freewheeling. And by the end of this presentation, I hope you have a lot of new questions, which I or any other of the E-leads will be happy to answer. So first, why? At its core, a buck converter takes something from a higher voltage and puts it at a lower voltage. So you can see with this clever example with big Adi being converted to little Adi, it's kind of embodying the whole higher to lower kind of idea. So I thought it was a nice, funny thematic element to add in. Okay, but let's talk about linear versus switch mode supplies. So I know that some of us might zone out because I know I personally would. So I highlighted in green the things that I think are important. So if you're going to read anything or listen to anything I say, at least pay attention to that. Linear supplies, we've seen them before. We've seen them in ISIN. So you could think about your resistor dividers where you have two resistors in series and we're extracting a voltage out in between those two resistors. What's happening is we're dissipating some of V in over resistor 1, and then we're dissipating the rest of it over resistor 2. And we're extracting some value at V out. But all this energy that's being dissipated on resistor 2 is lost. We've lost it to heat, we've lost it to resistance, it's gone. We're never gonna get it back. Another type of linear supply is a linear voltage regulator, which you might find on some of the PCBs on the formula car. Super simple way to regulate voltage, low complexity, low cost. But it has a similar problem. And I think this diagram illustrates it very well. You have your V in, and you have some current flowing through it to your powered circuit and to ground. So whatever's flowing to your load, your I load, that's going to your circuit. Cool, it's being used effectively. But the rest of it is flowing straight to ground, which means it's being lost. Lost to heat, lost to resistance, it's lost. We're not getting it back. Okay, cool. Why does that matter? Let's talk about efficiency real quick. And I'm just gonna show you this graph, and then we'll talk a lot more about efficiency later in the presentation, but I think this is important to get out of the way. A linear regulator has a linear efficiency curve. as its name would suggest. So if we're dissipating 40% of our energy, we get an efficiency around 60%. And that's kind of what we have illustrated here. With a switching converter, it's not quite linear. We have a more complicated kind of response for efficiency. And we'll see why that is in a little bit of time. But key idea here is that switching regulators are significantly more efficient than linear regulators. I'll leave that up there so everyone can just take a quick look at it, jot it down if they need to. And I'm going to move on. So who cares about efficiency? The answer to that is we do, and so does everyone else. And why does this matter for our formula team? Number one, batteries have finite amounts of energy. So if you think about our low voltage system, our low voltage batteries that are powering all of the boards, you know, the service section, LV box, sensing, dashboard, all of those, it's being drawn from these low voltage batteries. And they have a finite amount of energy. So if we're inefficient with how we use it, being shown by Neil over there, but it's finite. If we are not efficient with how we use our energy, it might run out before the race is over, and then our car just shuts off. That's not good, because we don't want the limiting factor to be something as small as the low voltage system. We also care about efficiency because when we lose energy in these transactions, it usually leaves us heat. And heat is not good for our components. They can only handle so much. It's not good for us, because if we're on fire, that's not good. Heat is generally bad. So we try to avoid introducing extra heat into our system. And also, there's some bragging rights when you have high efficiency. The power electronics world, high efficiency, that's some clout. So we try to get that as high as we can. So let's talk about the buck. I have abstracted the buck greatly, and I'm going to talk about why in a second, but at its core, the buck converter is a switching regulator. So we talked about switching regulators and how they have higher efficiency. That's because they operate on the principle of switching, i.e. turning themselves on and off very quickly. So if we take a voltage source, let's pretend it's our battery for the formula car, and we have a switch, and we have our load. How we can imagine a buck working if it was just a switch is that we're turning it on and then off, and then on and then off, and then on and then off, and then on, over and over and over again. You can see this time scale being super small, like microseconds. So this is happening super fast, like megahertz frequencies. Real quick, what we call the amount of time it's on over the total period is called a duty cycle. So in this case, you can see that the converter is on for 3/10 of the time. So we say it's a duty cycle of 0.3. Duty cycle is what percent or what fraction of a period is the device on. So this graph kind of illustrates that. Your T high is on, and then your T cycle is the entire period. Just wanted to make sure that was super clear. It's one of those vocab words I wanted to make sure everyone took away from this. How long is it on? Okay, back to this. Let's add some filtering, because if you look at this waveform, okay, let me take a few steps back. On our formula car, we have a 12-volt battery, and all of our boards are compatible with 5 volts, which is not 12 volts. So we want to be able to step down that voltage, right? Our components can only handle 5 volts. Some of them can only handle 3 volts. They definitely cannot handle that 12-volt input. So we want them to only receive 5 volts. And if we turn the switch on and off super quickly, they'll feel that 12 volt, 0 volt, 12 volt, 0 volt. They feel every single bump in your signal. So we want to try to limit that. And that's why we introduce a filter. So I've added an LC filter here, which stands for inductor capacitor. And it's a low pass filter. What's pretty gnarly about these is that when you stick it on your circuit, you can see that instead of having your huge jumps up and down, your voltage steadily ramps up to your expected 30% of your duty cycle. Remember that 30% duty cycle we had? But, big asterisk, if you zoom in and you make your timescale super tiny, you still see the switching waveform here, because at its core, we're still turning this converter on and off very quickly. So we want to remember that we're never going to get this down to 0, but we could try to make it as small as possible. This is called the ripple. Ripple, we'll talk about a little more later, another key word that I want you to take away. Key takeaways from this slide: filters clean up the signal and reduce EMI. I'll talk about EMI also in a little bit. EMI stands for electromagnetic interference. Okay, let's talk about filters super briefly. I want to compare an RC filter, which you've seen in ISIM, with an LC filter, which I'm introducing here. RC, resistor capacitor, LC, inductor capacitor. Resistors are lossy components. We call them lossy. And inductors, ideally, are lossless components. And what that means is that resistors have relatively high resistances when you pass voltages through them, which means that we're dissipating energy, we're losing efficiency. But when we have this inductor here, we're losing less energy because there's less resistance in the system. There's less energy just being dissipated as heat, which is something that we really are trying to minimize here. Another cool thing about these filters is that the slope. If you look at the Bode diagram for your RC filter versus the slope of your Bode diagram for your LC diagram, the slope is much steeper. It's twice as steep for your LC filter, which means that it does a better job of squashing the frequencies that you don't want in your system. Because that's what your filter is doing. It's reducing the amplitude of unwanted frequencies. So LC filter, less losses, and better squashing of unwanted signals. Okay, we've been talking about a switch.
Adi,
Yeah.
why wouldn't you always use an LC filter then?
In general?
What's the benefit of an RC filter?
So one reason I could think off of the top of my head, I'm not an expert on filters, but inductors are generally more expensive and more complicated. They have their own problems with circuits, with the response that I'll talk about in a second, as well as actually getting the correct inductor value is kind of difficult. Whereas with the resistors, they're super easy to find. There's all sorts of ranges for them, but inductors are more limited in your selection. So you might not get the exact filter that you're trying to design for.
Cool, thanks.
Yep. Okay, so we've been talking about switches. And before I had it represented as like a literal switch that you like turn off and you turn on. But realistically, that's not happening because we can't do that 1,000,000 times per second. It's not possible. So I'm introducing a MOSFET, which stands for metal oxide semiconductor field effect transistor, which is a mouthful, but you only have to remember the transistor part because that's what this is. And I'm going to abstract what a transistor is pretty greatly for the simplicity of this presentation. We're using it as a powered switch. We can control whether they're on or off with an input signal. So you can see our control here, controlling the gate, and that's basically connecting this terminal with this terminal. We can turn them on and off very fast, which is really good for this application. But something we have to remember is that they're very fragile. And I'll talk about why that's a problem in a second. Key takeaway, these are controllable switches that we're introducing. Okay, cool. We've upgraded our switch. We have our filter. Let's turn this bad boy on. Ah, shit. Yeah, if you turn your circuit on as is, MOSFET and LC filter, your MOSFET's gonna blow up. Which probably not what you're going for because I lied a little bit. Quick recap on inductors. Inductors have this property called self-inductance on the coil. So when you pass current through it, the inductor acts like an energy storage device, and it begins to store some of that energy in the form of a magnetic field. We could represent the voltage across an inductor with this equation, V equals the inductance times the change in current over time. So let's remember that, and let's take a look at the next slide. So ignore the diode for a second, and let's take a look at this inductor. When the switch is on, when the buck is in the on state, current is flowing through the inductor to your load, happy. But while there's current flowing through it, you're generating a magnetic field around this inductor. That magnetic field is there. And as soon as we open the switch, you have some stored energy here, and your inductor's like, whoa, the current is changing very quickly because it went from a lot of current to zero current. Let's take a look at our equation. If this change is very big, this is going to become very big because they're proportional. What that means is that all of a sudden we have the stored energy here, which turns into negative potential or a negative voltage across the inductor. And that's generated to maintain current flow because V is proportional to current. Now, cool, great, there's voltage. Now what happens? there's some voltage here that we don't want because that could cause a spike in our load. So our fragile, sensitive equipment can suddenly experience 10, 20 volts. That could short them, break them. But more realistically, more likely, our switch, our MOSFET, because it's closer and it's just as susceptible and fragile to these voltage spikes as any other device. It's kind of like, yeah, they're kind of like made of glass, if you think about it in that sense. So how do we combat this? We need some way to dissipate that energy. So we introduce a diode. These diodes are called flyback or freewheeling diodes. What they're doing is providing a path for your newfound current being generated from that field to flow through. So when your buck is in the on state, your diode is going to be off. Because if you look at it, the diode's pointing the other way. Diodes only allow current to flow in one direction for the sake of this presentation. Don't worry about what that means. But right now we're treating this diode like it's only allowing current to flow this way, up. So our switch is closed, our buck is on, current is flowing this way. We open it, and oh no, where does the current go? We don't want to go into the load. We need somewhere for it to dissipate. So this diode, which has very low resistance, is going to create this path for the current to flow through. What's cool about diodes is that they dissipate a lot of energy very quickly. Every time you go across a diode, you lose like 0.7 volts, maybe 0.4 volts for like a more efficient one. So we're dissipating that energy very quickly by just going in circles over here. And all of a sudden, this giant negative potential goes back to zero. And we're chilling, ready for the thing to turn back on. I'll illustrate this with a graph here. So this green line is the voltage of the switch. So let's treat this as off, turns on, turns back off, turns on. So you can see that when the switch is on, there's no current flowing through the diode. It's not conducting. But as soon as we turn it off, the current spikes because all that current is now flowing through this diode. And then you can see it dissipating the energy because the current drops super, super, super quickly. Drops from 4 amps to 0 amps in like 2 microseconds. So that just kind of proves, I don't know if you'll have a good grasp on what kind of scale that is, but that's a massive current drop in a very short amount of time. So that's kind of nice. That's what we want. Takeaway, that is a lot of words. We implement a diode to freewheel to protect against inductor-induced voltage spikes. That might have been a little bit of a jump, especially if you're not familiar with some of these components. Diodes protection. All right, cool. Real quick, I'm just going to add some input capacitance here as like a filter for our input voltage. Filtering is a huge theme you'll see on power converters, and it would be more accurate to represent this with an input capacitor. If you're more mechanically inclined, you might think of this as like a heat sink on your system, if you want to think of that as kind of like a filter or a way for your energy to be stored elsewhere. Okay, so there's a question over here. Why do we use a 12-volt battery for boards operate at 5 volts? Are there components that operate at 12 volts? So yes, a lot of components on our electrical vehicle operate at 12 volts. Some of our sensors, some of our buzzers, some of our lights, LEDs. Also, 12 volts is the industry standard for car batteries. So that's kind of like a cool parallel that we have between actual industry and our race car team. Cool. So back to here. Oh, man. We have this. How do we take it from a schematic to a layout to a finally built, tested, actual piece of hardware? So I'm sure all of us have seen this at some point in our lives. It's a design process. You have your requirements. We're taking a high voltage and making it a low voltage. We have some constraints. Maybe there's only so much current we could allow to flow through the system. Maybe we can't let it get too hot. Maybe mechanical only gives us 1 inch by 1 inch on our boards, and it's impossible to fit all the components in there, but we have to fit it in there anyways. These are all constraints we have to consider. And with that, we explore different options for how we design it. We make a design. We test it. Oh no, it's not perfect. We go back to design, test it again. Good enough. Design again, test, good to go. Okay, so what you do is you hop over to digikey.com, us.digikey.com actually, and you can search up buck converter, and you'll get hit with 27,000 results for your switching converter. And we're gonna want to filter those results. And we're not gonna filter them with your LC filter. You're actually gonna filter them with, sorry, bad joke. You're gonna filter them with these options here. You're gonna basically define your system requirements, like you want a 5-volt output, you want a positive output. There's a ton of different modes you could have. There's a ton of filters. Eventually, you do some searching and you find the one. This one looks perfect, amazing. So you say, all right, cool, what do I do with this? This doesn't look like an inductor. It doesn't look like a diode. What is this thing? It is an integrated Buek chip, and it's super sick, and it'd be super sick if we knew how to use it. So what we do is we look at the datasheet. The datasheet has a ton of useful information. Instead of having to come up with a complicated PID control loop to optimize our duty cycle for the perfect output voltage, this chip does all the hard work for us. And in fact, the datasheet tells us exactly how to use it. So it tells you what capacitors to use, what inductors to use, what resistors to use. Wow, it did all the design work for us. But let's say it doesn't tell us exactly what we need. What if we need something slightly different or something super specific for our application? We would take a look at the fine print. There's a ton of equations. You'll probably find like 20. And it's a very simple way for you to plug in all the values you know for your system to get out exactly what component values you need. So you could derive all of these with the equations provided in your datasheet. Super cool. If you're interested in how these chips actually do the controls, you could look further into the datasheet. I don't know if many people actually do that. Takeaway, datasheet, godsend, good stuff. We need it. Cool, so we have the schematic, and the datasheet even tells us how to lay out our Buek. Like it'll tell us, oh, okay, put your chip here, put your inductor here. Like this will reduce your noise. This is great for thermals. This is exactly how you should do it to have your perfect Buek. So we do that, and we've taken our rudimentary switch and load and turned it into a full-fledged Buck converter for our system. Nice. But disclaimer, this is the bare minimum, and it's usually not what your system needs. Is our Buck any good? We have to ask ourselves this question every time we make a Buck. So some of the metrics we use to make sure they're good, there's a ton, which is why I added ellipses, but some of the main ones are, we check the peak-to-peak voltage. We check the voltage overshoot. We check the electromagnetic interference. We check the efficiency. And then we check the volumetric footprint and the thermal capabilities. Those are some of the main ones. I'm going to touch on them very briefly. So peak-to-peak voltage. Remember at the beginning when we saw that zoomed in trace with that bouncing waveform? If you look at this, the peak-to-peak is 0.3 volts, 300 millivolts. For power converters, that's freaking massive. Because if you think about your CPUs inside your laptops, your Intel Core i7s, those things can only handle a peak-to-peak of about 10 millivolts. Ideally, they'd handle a peak-to-peak of around 5 millivolts. So we're like 2 orders of magnitude higher than we should be with this. So we got to get those numbers super small, and I'll explain how we do that in a second. That's peak-to-peak voltage. Next is the voltage overshoot. So sometimes our controller, which we are not controlling, gets super excited. They're like, yeah, we're on. So they turn on, and then the voltage ramps up super high, and they're like, oh, we overshot it real bad. And they overcompensate. They go way past where they should go. And they come back up, and then eventually they settle on the voltage they need to be at. So the control loop is never perfect. And sometimes this overshoot is just high enough that it'll break our components. Every component has a rating, a voltage rating. And if we exceed it, we could break something. EMI is the electromagnetic interference in our system. So there's 2 ways that is introduced. One is with our inductor, because there's literally a magnetic field being generated. That is magnetic interference being introduced to the system. The effects of that are pretty negligible on our formula car, but not in other applications. Something that we don't have to worry too much about. Second is the switching. We're turning a switch on and on super freaking fast. And what that means is that we're basically creating a signal, like a sine wave, essentially, with like a super high frequency, which is what antennas do. And antennas are not always good for our signals, and you'll see why in a second. Signal is a noise. Let's take a look at signal A. Let's pretend that this signal is saying hello, right? And then all of a sudden you have some noise. It's like psh, 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 or whatever, right? And it doesn't make any sense. And all of a sudden, when your signal and your noise couple together, instead of hearing hello, you hear hold on or something, and you don't hear exactly what you need, and you'll end up with something weird. So the takeaway for that is your electromagnetic interference is bad for signals. That's all you need to know. Okay, back to efficiency. We touched this earlier, I'm gonna touch it again. We calculate efficiency with this equation. Efficiency equals power out over power in. It's a pretty simple equation. I stole these screenshots from our Buek data sheet, and it basically tells us at specific currents, our Buek's efficiency is noticeably higher. If you look at this at 1 amp, high efficiency, 1 amp, high efficiency, 1 amp, high efficiency. So if our system calls for 1 amp, we should definitely use this converter. If our system calls for 0.5 amps or 0.05 amps, you can see that the efficiency starts to drop off, and it drops off super quick. So we have to make sure that we're really designing for our system and not just like picking a random Buek just because it looks good or it's cheap or something. So takeaway from that is you'll enjoy higher efficiency if your Buek complements your load. If you're not familiar, your load is what determines what the output current is. Okay, this part gets a little bit hairy, so I'll go through it quickly, but be as descriptive as possible. We have our MOSFET. Our FET is this transistor, it's a switch. And when it's off, there is a high voltage difference between your two terminals, and when it's on, there's no voltage difference between your two terminals. When it's off, no current is flowing, and when it's on, current is flowing. So let's take a look at what those look like complementary. Our switch is off. The voltage difference between your two terminals is high. But we turn it on, and it's not instantaneous like the simulation showed. There is some time where it has to turn off and the voltage drips down to 0. At the same time, the current ramps up from 0 and goes to some value. If you remember, P equals IV, power equals current times voltage. There is some power present here, and that power is dissipated in the system. So we'll see losses when we turn on the switch and we turn off the switch. Also, when it's on, there's no such thing as a 0 resistance component. So there'll be a little bit of conduction loss because you have your resistance and you have your current. Just stuff to remember. That's a big source of losses. I never found a graph for diodes, but diodes also dissipate a lot of energy, especially in that freewheeling state. Remember when the current was going around that diode a bunch of times? We're losing energy in that transaction. Just something to remember. Okay. We could even upgrade the Buek topology. We could go from 1 switch to, wait for it, 2 switches. Wow, amazing. We've gone from our asynchronous Buek to our synchronous Buek. There's a ton of differences. There's a switch versus a diode now. The complexity is increased because we're controlling 2 switches instead of 1 switch. The cost is increased because we have different components now. The controls are more expensive. Maybe the semiconductor cost is higher. Now we're experiencing different types of conducting and switching losses because now 2 things are switching on and off, but this diode's not there to dissipate energy. So we're noticing overall changes in efficiency. Takeaway, you can get more fancy. This is the bare minimum. This is like the next step up. Why that's cool is that with this stepped up synchronous Buek, you can see that at our ideal current, 1 amp, like we were talking about earlier, there is noticeably higher, like 10% more efficient efficiency, which is cool. High efficiency, good stuff. We like that. We can improve our filters. So I talked about filters earlier. We slapped on a ton of capacitors. We could reduce the equivalent series resistance in them because every component has some resistance in it. Your wires have resistance, your transistors have resistance. Nothing is 0 resistance. So we experience losses there. We could try to minimize that. We'd also squash unwanted frequencies. So with better filtering, remember that larger negative slope with the LC filter, maybe we could eliminate more of those unwanted frequencies. And we could reduce the effects of electromagnetic interference. So we'll get those nice hello messages instead of other stuff. Okay. This quote is the most important thing I'll tell you today. And this graph is the most complicated thing you'll hear today. But I think they're both important, but this quote is definitely the most important thing. And that is, impedance is resistance at different frequencies. And I've heard this several times, but it never really made sense to me until this year. So it might take a little bit of time for it to lock in. High frequency is some crazy shit. Like, I don't understand it, and I don't know how people mess with it. But at the end of the day, your components will not behave the way you expect them to at higher frequencies. So let's take a few steps back and talk about capacitor selection. This is the buck on our formula car for most of the boards on our formula car. We have a few variations. There's not one input capacitor and one output capacitor. There's a few of them in parallel. And capacitors have this cool property where if you connect them in parallel, they work together in an interesting way. So if you take a look at this graph, impedance versus frequency. The impedance is something we're trying to minimize at our operating frequency. So remember, we're operating on microseconds, so around 1 megahertz. We want to minimize our impedance at 1 megahertz. And each capacitor has different curves for how they behave at different frequencies. And these aren't specifically the ones on our formula car, but these are just as an example. When you have all of these put in parallel, they kind of superimpose on each other, and you have this new superimposed curve, which has a minimum at 1 megahertz, which is where we're operating. So we put them together, we have a better filter with less ESR. That's kind of all I want to talk about in this slide. Yeah. So I talked about a lot. We started with something simple, and I suddenly threw a ton of different things at y'all. So we have to ask ourselves, when is enough enough? We could settle with our simple switch diode configuration, or we could go to a fancy PID controller to minimize output ripple, or a multi-stage to handle varying loads, or there's so many different variations on power converters, like I couldn't even begin to explain it. But there's a ton, and we have to decide when to stop. Usually the limiting factors are the amount of space you have and the amount of money you have. Because if you're producing something on the order of 10, like our formula car, like we could shell a few extra dollars. But if you're making 1 million of them, that's going to add up super quickly. Tons of considerations, just keep some of that in mind. So I'm just going to touch on this quickly. I kind of mentioned it. This is the formula buck. So let's look at some of those parallels we see here. We have some extra stuff. This little guy here is reverse protection. It's how we protect from connecting our battery in backwards. This is an indicator. It tells us when we have a battery connected. This is an indicator. It tells us when we have a stable, solid output. And the rest of it is our buck. It's a little bit different from what we've seen, but there's some elements that are the same. You have that LC filter, which is really the heart of the buck. You have your switch, which you can't really see here because it's inside the semiconductor. Interestingly enough, there's no diode. Don't let that confuse you. Don't worry about it. I'm just making sure y'all know that it's not there. And there's some other bits and pieces, but you have your output capacitors, input capacitors. We're taking 12 volts and we end up with 5 volts. Cool. So to reiterate what I showed you at the beginning, this is what I hope you got out of this presentation. I know it was quite a bit and I went quite a bit over time, so thank you for your time. Understand the general concepts of linear versus switch mode power supplies, parts of a buck converter, and define some of these terms. And right now, I'm happy to answer any questions, but if y'all gotta go, you can go. If you think any of these concepts are unexplained very clearly, I'm happy to roll back a couple of slides or just walk you through it as a group or one-on-one. Oh, nice. And calling out of this. So there's a feedback. So please leave me feedback. Feedback is good.
Yeah, please fill out the feedback. And then also just so you know, I'm typing up answers to all the chat questions I got, and I'll put those in a doc and share that, and also send them to the specific people who asked each question. And then if you have more questions from the answer, I'm happy to Zoom call with you or Slack back and forth or whatever.
I also tried recording. So hopefully these have saved to my laptop and I can stick them on the OEM YouTube. So you can watch